Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at ways that we use partial derivatives to evaluate thermodynamic properties. Our goal is that you will have another opportunity to use these differentials and partial derivatives that help us write expressions for changes in these important thermodynamic properties, and then use mathematical equivalencies to modify these resulting expressions to put them in terms of measurable quantities. Now recall that we have our energy fundamental relations. For a pure system and a closed system, we have du equals TdS minus PdV, dH is TdS plus VdP, dA is minus SDT minus PdV, and dG is minus SDT plus VdP. And if you have a mixture, then you would add the sum of the chemical potentials times d in I for each component to these expressions. So these other energy functions are defined as H is U plus PV, A is U minus TS, and G is H minus TS. From these, for a system that is either intensive, pure, or in a closed system pure, we get the full set of Maxwells shown here. And we've looked at how these can be derived, and we also know that we can involve mixtures also. But this is the set that we're going to be looking at today for pure substances. We have several math rules that we need to use. The first is the reciprocal rule, and we have the triple product rule, and the second derivative rule that says that because these are continuous functions, we can take the derivative in either order without having a change in the meaning. Finally, our last tool we need is the set of measurable quantities. So we can easily measure pressure, volume, and temperature. With a bit more effort, we can measure specific heats at constant pressure or constant volume, and they are defined as either Tds dt at constant P, or dH dt at constant P, or Tds dt at constant volume, or dH dt at constant volume. We also have an isobaric compressibility beta, which is how volume changes with temperature. And then the isothermal compressibility kappa is the negative of 1 over V dV dP at constant temperature. So all of these things could be directly measured. Let's look at how we might use these tools to solve a problem. So let's look at how does temperature change with pressure in an ideal insulated pump or compressor. So if it is ideal or insulated, then we are talking about being reversible, would be our ideal. And insulated means Q is 0. Therefore, this path is isentropic. So what we're asked to find here is what is dt dP for a constant entropy path. So how would we do this? We know that we have dt dP at constant S, and when we have entropy in the path, using the triple product rule is a useful way to get the entropy out of the path. So I would use the triple product rule in this way. Okay? The next thing that I would like to do is I'd like to really get rid of the entropy. Entropy is always sort of a problem. And so the way that I can do that is first to use the reciprocal rule so that I have S in the numerator on this expression. So therefore, this would be ds dP at constant temperature over ds dt at constant pressure. ds dt at constant pressure, perhaps you recognize as being from the definition of C sub p. So therefore, I can say that this is T over C sub p, because it's in the denominator, times this negative ds dp at constant temperature. And next, to get rid of ds dp at constant temperature, it isn't on my list of measurable quantities, but it is in my list of Maxwells. And so I can use the Maxwell that says that negative ds dp with constant temperature is dv dt at constant pressure. So that took care of the negative sign also. And finally, I now dv dt at constant pressure. I could use this, or I can use the definitions of the measurable quantities, and I can use the isobaric compressibility to turn this into beta Vt over C sub p. Now both of these last two expressions are technically measurable, but they have different applications. So what we want to do next is we're going to then look at how we could evaluate these expressions. So let's look at case 1. If we have liquid water being fed to this pump at 20 degrees C and 100 kilopascals, the properties under these conditions are that the specific volume is 0.001 cubic meters per kilogram, beta is 207 times 10 to the minus 6 reciprocal kelvins, kappa is 4.5 times 10 to the minus 10th reciprocal pascals, and C sub p is 4.18 kilojoules per kilogram Kelvin. And so what we found is that dt dp at constant S is beta Vt over C sub p, which in this case is 207 times 10 to the minus 6 reciprocal kelvins. The specific volume is 0.001 cubic meters per kilogram. The temperature is 293 Kelvin. Be sure you use absolute temperature. And C sub p is 4.18 kilojoules per kilogram Kelvin. So my per kelvins cancel out, per kilogram cancels out, and I have meters cubed, kelvins, and per kilojoule, kilojoule still left. So what we need to know is that 1 kilojoule is equivalent to 1 kilopascal times a cubic meter. And so therefore I'm going to have those cancel out, and I'm going to be left with units of Kelvin per kilopascal, and in this case 1.45 times 10 to the minus 5th kelvins per kilopascal. So it would require an incredibly large temperature change, or pressure change rather, to get even a noticeable temperature change. So delta T is going to be very, very small, right? What about if I look at this other case where I have carbon dioxide coming in at 20 degrees C and 100 kilopascals? And let's assume it acts as an ideal gas. The volume is 0.544 cubic meters per kilogram. C sub p is 0.8459 kilojoules per kilogram Kelvin. C sub v is 0.6523 kilojoules per kilogram Kelvin. So this is the data that I was able to find for CO2. Now, I don't have beta in this case, but what I do know is that if it behaves as an ideal gas, then V is RT over P for an ideal gas. And so dV dt at constant pressure is going to be R over P. So when I did dt dp at constant S, I could say it's beta Vt over C sub p, but I also could say it's T over C sub p times dV dt at constant pressure. So that says it's RT over P C sub P. And from the ideal gas law, that means it's the specific volume over C sub P. So I have this information. V is 0.544 meters cubed per kilogram, and C sub P is 0.8459 kilojoules, but we can just do this from that unit conversion we just saw. A kilojoule is a kilopascal times a cubic meter, and then per kilogram per Kelvin. So the cancellation, I'm going to be left with an answer of, let's see, 0.643 kelvins per kilopascal. Now, that's a much, much larger number than what we had a moment ago. I mean, orders of magnitude larger. And just kind of generally a compressor, you never want to compress to more than 3 times the feed pressure. So let's say that I go to P2 of 3 times, so 300 kilopascals. So delta P, therefore, would be 200 kilopascals. And if that's the case, then delta T is 129 Kelvin, or 129 degrees C. Wow, I mean, that's huge, right? And so that's why when we compress gases, we don't compress them to very high pressures all at once jump, and then we usually do some cooling of the gas before we would compress it in the next stage. So this concludes this example. Thank you very much for your time.